operations are closed, then, so it exists a set.
Good luck.
Is that for you? Then the set V along with the two operations is a vector space. So there exists some set such that if the two operations, any two operations they give me, if they're closed, then the set along with these two operations forms a vector space. Does there exist such a set?
Can't that be non-empty or empty?
Rather no zero.
Yeah, so hands up for true. Okay. Hello.
Is that a full ass meal?
You have a mukbang in class. Okay. So hands up for true. Hands up for false. Okay. So this is true. If we just take the 0, and then if it's closed, if your two operations are closed, then all the 8 axioms will follow.
Isn't that like by sort of how we characterize a vector space anyways?
No.
I mean like if they're closed under the two binary operations, usually
Yes.
any addition of vectors and scalar multiplication, right?
Yeah, but then the other 6 might not follow, right? As we showed in our first assignment. So we might have checked that it's closed, but then it might not follow that the rest holds, right?
Okay.
So for example, B over A, right?
And
So you guys showed that that's not commutative. Okay. Question?
Since this says there exists, do we have to construct the set?
Yeah, you just show that there exists a set. And I just showed it to you.
Any,
What is it?
we can just
What's vector space, not subspace?
One at a time, sorry.
We can do set of all real numbers or.
But if you do the set of all real numbers, you're gonna have to show that for any two operations such that those operations are closed, which is gonna be like impossible, right? But you can show this for the zero vector. Okay? I think this is it for subspaces. We shouldn't go further than this.
Just a quick question.
Hands up?
Yeah, don't we use the remaining other axioms?
Yeah, my claim is that the remaining other axioms will follow.
Okay.
Like so long as it's closed, they would follow. And I'm saying there exists a space or a set such that this holds. And yes, the set is
So when
just
close, it just satisfies 8 axiom.
yes, the 8 axioms will follow from the closure, is what I'm saying. Okay. Do we all get what the question is trying to say? Yeah. Okay. This is just a warm up. Getting into the fun stuff a bit later. Okay. So the second part of the course, we took span and spanning set.
Joel, sir? Is that an S or a G?
Oh no. Now? Okay. This is a G.
Okay.
Because it wouldn't make sense for us for me to say spanning set, right? Yeah, spanning set. Question? Okay. So, do I need to define these or are we all good with these definitions?
We're good.
We're good? Okay, one spoke for everyone else, but I think we're good. Okay. So again, true or false? Yeah.
True.
So I'm saying if S is any set of vectors in some vector space V, then S is a subset of the spanning list.
They draw the coordinate 1.
Hands up for true.
Sure.
Okay. This one's straight from the definition of spanning set. And then another one, true or false. Oh, you just let something be here and then show that it's in here. Right? But you could do that by just picking one for all the constants, right? Okay, true or false, there exists an S such that what's this? What is this actually saying? It's saying that there exists some set such that its span is equal to itself, because this holds for everything, and so if this holds, that means we get equality. True or false? Hands up for true. Who wants to give me the actual set?
Zero.
Yeah.
Empty.
Okay. Next step is linear independence and linear dependence. So, true or false, length of linear independent set is less than or equals to length of linear independent set. I guess it's not right up there. That's right, length.
You mean the cardinality?
Yes. Yeah. Length, cardinality, size, dimension. Well, dimension's iffy, so let's not use that for now. But is this true or false? Hands up for true. Okay, hands up for false. Okay, so it's like a bit split on the middle. This is actually false. We got a celebration here, that's good. Okay, why is this false?
1, 0, 0, 1, no 1.
Wait. Can I get a non-trivial example, maybe?
1, 0, 1,
Okay.
0, 1, 0, 0, 1.
1, 0, 1. This is one set. Okay. And then
1, 0, 0.
1, 0, 0.
0, 1, 0.
Okay. 0, 1, 0.
And 1, 1, 2.
And then our length of the linearly dependent set could just be 2, 0, 0, and then 1, 0, 0. Right? So there's zero relation between these two, independent and dependent sets. Right? But there is, when it comes to length, yes. But there is a relation when it comes to the spanning sets and the linearly independent sets. And that sets up a lot of things when it comes to determining the length of a basis. And most of the proofs when we're proving stuff about bases follows from this. I'm gonna frame it as a true or false, but you guys should all get this, right? So, we can say cardinality. Hands up for true.
What a coordinate.
It's just like the size, the length. Hands up for true. No, we need confidence for this one. Yeah, hands up for true. Everybody raise your hand. Okay, hands up for true. Yeah. This is something that you guys should know really well. Theorem. Theorem.
I think it was 202.
How I
There you go.
if you
Theorem
test whether
2.02.
how I write.
What is it?
How I prove this.
How do we prove this in our tutorial?
That's it.
It's in the
By
notes
theorem.
somewhere.
It's in the notes too, yes.
Wait,
Okay.
wasn't that the one Florian wanted us to prove for the, he said, it's gonna show up on the midterm, and then I didn't spot it on the midterm.
It was on the makeup midterm.
Where it was? I don't remember.
I remember. It was on the makeup midterm, and then I learned my lesson.
Do you have a question?
Yeah.
Yeah.
Can we get a counterexample, like a counterexample for the first one?
Oh, we just did. So you can take the standard basis for R3. That's your linearly independent set, and then your other set, your linearly dependent set, could just be 1, 0, 0, 2, 0, 0. Right? This is linearly dependent, but then the standard basis for R3, which is in fact linearly independent, has larger length or size or cardinality. I think it's best to use cardinality, like your peer said. Yeah. I'm sorry, I can't hear you.
It is assumed that both of those sets are non-trivial in the second. Like, spanning.
Oh yeah, but the spanning set can be empty unless we're talking about the zero vector space, right? Yeah, so I might have had to add non-trivial vector space. So let's be okay. All good. All right. Okay, we're gonna skim quickly past the next part because I think the notes does a really good job of covering it, which is linear systems. And I don't think when grading the assignment and the midterm, most of you guys got questions about this grade, so it was fine. Okay, can anyone tell me what it means to be consistent? Yes.
At least at one position.
I'm sorry?
At least at one position.
So, there's this, at least one solution to A x equals B, and then inconsistent. What does this mean? Okay, and if you guys want a good resource for true and false questions for this, exercise 1.8.6 has more than enough that you can practice on. Go through it yourselves and see if you guys can get it.
For linear systems that have many solutions, are they called non-consistent? Or
What is it?
for linear systems that have many solutions, what are they called?
Also, if we have, yeah, this says at least one solution,
Okay.
right? So just as at least one, we gotta think of many.
Is inconsistent system dependent or independent?
Inconsistent means we have no solution, and that's characterized by when we take our augmented matrix H and row reduce it, we get a column, or sorry, a row of all zeros at the bottom. Okay? Okay. Work not being used. Okay, could anybody tell me the difference between a direct sum and direct product? Kyle?
Actually,
No.
no. I mean, I was gonna say something like somewhat stupid, but if you still wanna know.
Okay.
I was gonna say one is like adding, one is like multiplying.
That's like 0.5 out of like 40.
Wait, what?
Direct sum is like each vector is made up of the vectors of like D and W, and the direct product is more like the tuples are like, for example, like the direct product of R2 and R3 is R5.
Okay, yeah, so he said it perfectly almost. But there's one condition that we have to impose on a direct sum. So we can't have a direct sum without having a condition, which is, yeah?
The only vector they share is the zero vector.
Yeah, thank you. So direct sum would look something like Wi is a subspace of V for all I equals 0, whatever n, and then Wi intersect Wj is equals to 0 for all I, comma j equals whatever, and then the direct sum would be okay, and this will be equals to the set that looks like this: W1 plus W2 plus Wn, where W1 is in big W1 all the way, Wn is in big Wn. Okay, so this is direct sum. Now direct product, as your peer said, would look something like Wxv, where those are two vector spaces, okay? So vector space is equals to VW, or I should have said WV, V, where W is in W, and V is in big V. Okay? So you just have to note this difference. It's not too hard, I think. Questions about direct product and direct sum. I wouldn't expect any on the final. I'm just trying to go through all the notes so you guys have a recap of what we went through. Okay.
So direct sum equal what?
Question?
Is direct sum equal what?
I'm sorry.
Is direct sum equals what?
Equals what?
Is W1 plus W2 plus Wn equals?
Yeah, like, so the elements of the direct sum are of the form W1 plus W2 plus W3 plus W4. So you're just adding elements of your respective
It
subspace.
equals the subspace. Or when it's
Not of the whole
it's part of it. That would be the sum.
not for all.
Okay, let's do our first proof.
Not for all vectors.
It could be for
Can I erase all these boards? Yeah? Okay. Okay, now the next stop that we made in our course is basis and dimension. And so, I'm not gonna write out any definitions in this seminar because I think we're just wasting time. You guys can look them up on your notes, so that's fine. But let's have a theorem. This is one of the problems that you guys had to solve. Theorem. Okay, so we're gonna prove this. I'm gonna prove this direction, so I'm gonna prove the reverse direction. And if you guys wanna practice, you can prove the forward direction, but I don't think that's too hard, at least in comparison to this reverse direction. Okay, so we wanna show that, if x intersect y is equals the additive identity 0, then the dimension of the direct sum x plus y is equals to dimension x plus dimension. Okay? So how can we start? Yes.
Basis. You start, since x intersect y is only the zero factor, they both have their independent bases and their own, which span their like different dimensions.
Okay, so like we have a basis for x, we have a basis for y, and okay, that's a good start. So we have that this is our supposition, right? This is what's given to us. So suppose okay, as Kyle said, let B1 be a basis for x. And then B2 be a basis for y. Okay, so let's look at what we actually want to show. We want to show something about dimensions, okay? And now this implicitly gives me two things about the dimensions of x and the dimensions of y. The dimension of x is going to be n, so therefore dimension of x equals n, I remove this, and so dimension of y we want to show that the dimension of x plus y is equals to m plus n. Okay. I made a note earlier when I was talking about spanning sets and linear independencies, and then the true or false that I presented. I said when we want to show something about dimension, we typically work with bases, but when we work with bases, we typically work with sets and trying to show that they're both spanning sets and linearly independent. Okay? So, how can we move forward from here? Yes?
Is the dimension of x plus y? Like if you write that as dimension and then just write both sets as one?
So you're saying we take this?
Yeah, you can write that out as like the span of x, the set of x and y spaces.
Okay, yeah, you have the right idea, but I think we're skipping a bit of steps. But like that's what we're gonna get to. So yeah, good idea, but yeah.
Can we write x as span of B1 and y as span of B2 and this sum will be span of B1 comma B2, I mean, like that.
It won't be as direct because we kind of have to make sure that there's no overlap, which is kind of implicitly given to us by this, but that's also a good idea. Maybe something about extending bases. You're gonna say?
Yeah, I was gonna say, we take the arbitrary vector in x plus y and then write it in terms of B1 and B2.
That could work as well, yes. Okay, so for this, so we have our right hand side, m plus m. We have the x plus y is this set. Okay, and so we need to show two things. We need to show that one, this set right here, is linearly independent. And then two, we need to show what our colleague over here said, which is that it does span x plus y. So this is 1, 2, span of x1, xn, y1, ym, and we'll correct it on this, is equals to x plus y. Why do we want to show these two?
Expansion LI.
And linear independent gives us
Bases.
gives us the basis, yeah. And so basis gives us dimension. Okay, and this is of cardinality n plus m, and we want something of size n plus m, right? Okay, so how do we show the first one? This is standard in this course. I mean, we've done it a million times, maybe more. So how do we show something is linearly independent? Yes, Kyle? Kyle?
Show that like it spans zero if and only if the scalars, for which you multiply the bases first, the vectors there, are all zero.
Thank you so much. Okay, so did everybody hear what Kyle said? So we want to show, so for one, I want to show that first let's have some scalars first. So let alpha 1, alpha n plus m be scalars in our field. So I want to show that alpha 1 x1 plus alpha n xn plus alpha n plus 1 y1 all the way to alpha m plus m ym equals 0 if and only if alpha I equals 0 for all I equals to 1 all the way to n plus 1. Okay. That was like a mouse, she sells seashells by the seashore. Okay. Let's get this down. Can we all see the board? Can we all see what's written here? Because I kind of crunched it at the end. Yeah? No?
Right bigger. I actually cannot.
Okay, yeah. Okay, sure. Kyle's that one guy that stops the barber while he's cutting his hair. He's like, I don't like it. Yeah. Wait a second. I'll write it here. For all can we see it now? Oh, can we see it?
Yes.
Yes? Sometimes you just have to say yes, even if you can't. You just say yes, we can move on. Okay? And if you have questions, ask me. It's recorded, okay? Because I know this is not the full class. So there are people that are not going to be here. So yes, it is recorded.
What about the online?
About what?
The online ones.
The online ones, I don't know, I'm not running them, so I can't really tell if they're recorded or not.
Okay.
Yeah. Okay. But how do we know this is 0? How do we know all of our scalars are 0? So I'll continue the proof over here. How do we know all our scalars are 0? So, yeah.
You move like all of the y to the other side, so like the span of x equals span of negative y, the negative span of y, and that can since they don't share they only share one vector.
Oh no, wait, that's not a plus. Yeah, sorry, I thought I was missing something. Yeah.
Yeah. So
Yes.
and since they only share the 0 vector, that means they have to be 0. And since they're both linearly independent, it can only be 0 when it's all 0. So
Perfect. Perfect. That was a perfect answer. Okay. So we have alpha 1 x. So this is true if and only if alpha 1 x1 plus all the way alpha m xn is equals to minus alpha n plus 1 y1 plus alpha n plus m y m. Okay.
shouldn't that be shouldn't there be graphics or like
Negative. Yes. Yeah. Well, our scalars are just random scalars, so it doesn't really matter, but yeah, in this case, you're. And this is true if and only if alpha 1 alpha n plus m equals 0, since x intersects y is only the 0. Question?
We need to write it on this way because we know that x and y are both 0, and we know they're both base. So doesn't that just imply that they're going to intersect already? Like we have to do it.
Yeah, but you have to show it. That's you're implicitly giving us what the question is trying to ask you. Because if that's an extra given, you're adding a hypothesis to what the question is asking. That's also a problem that many people had in the assignment, the most recent assignment especially. It's like they give me the question that we're asking after we asked it to them. You know, like it'd be like, suppose what we want to show, then what we want to show. I mean, yeah, right? Yeah. Like this is what we want to show. We want to show that this is actually true. Right? We want to show it is linearly independent. Because that's not a theorem that we have at our disposal. Right? It might be, but not on the test. Yeah. Yes. Okay. So do you get how we moved from here to here? We just moved to the other side by algebra, and you guys have to write maybe by algebra. I don't, because I'm not getting graded. So you put the negative sign here, and you say by algebra, and do we get that?
but you have to write by algebra or
I mean, I think you do. I'm not sure how strict Corey is with grading about that, but I know in A37 we do, so I assume. I know A37 has a lot. It's not funny there, you're torturing them. Okay, so we get why we reached here. Yeah? Christina? Yes. Okay, and so we know that the intersection of x and y is 0, right? By the given. And so we know that x1 to xn spans x. That means the span of x1 to xn is equals to x. And we know the span of y1 to ym is equals to y. Right? So the only thing they share is 0, right? Got it. Nice. Okay. And I knew somebody that did. Yeah.
Why is that implies that our guy is in both vector spaces?
Because this right here means this is in the span of y1 is in the span of x1 to xn.
Okay.
Yeah.
Why would you move the span y to outside?
I just use algebra. I just moved it to the other side, right?
Why?
Why? Because I want to argue that the only thing that they share is 0, so that we can make these 0.
The one saying since x and y is 0. You already showed that.
No, I didn't show it. I'm trying to explain to her why this holds. So do you get why like this means that this is in the span? Yeah, so it's an element in the span. Yeah, and so that means the span of y1 to ym is equals to y because it's a basis, right? And the span of x1 to xn is equals to x because it's a basis, right?
Yeah.
And so that means we're saying this thing is in x and it's also in y, but the only thing in x and y is 0, right?
Okay,
Right?
yeah.
So informally speaking, left hand side is in x, right hand side is in y, or left hand side equals the right hand side, so it's equals to 0. Okay, just informally, this is not something you should write, just read the intuition, because I guess I might have lost some people on that side. Okay, so we showed what we want to show. We showed the first thing that we want to show, which is that it's linearly independent. And now we want to show that it's a spanning set. How do we show that something's a spanning set? Yeah, you're right. Did we all hear Sophie? So how do we show that something's a spanning set? So we just showed that our set is linearly independent. We want to show that it's a spanning set. Yeah?
Taking arbitrary vector of x plus y, y, and show that it's including this, that it's including the spanning set.
Yes, it's included in the span of what we want to show is a span. Yeah. Oh, can I erase this by the way before? Okay. Let's record it. Okay, step number 2. I want to show that, let's call it a B3, or just B, equals x1, xn, y1, ym is a spanning set. Of x plus y. So, as your colleagues recommended, let's take an arbitrary element in here and show that this spans it. So, let x plus y be a small x plus y and big x plus y. Okay? We want to show there exists scalars in our field. Whatever our field is, let's call it F for now. Alpha 1 to alpha n plus m, such that the sum n plus m, or we don't need to do that. Alpha 1 x1 plus alpha n plus m y m is equals to x plus 1. Do we all get why we need to show that? Yeah, just definition of a spanning set, right? Okay, and so since we let x plus y be in big X plus y, how can we show what we want to show? How can we show that there are scalars that actually give us what we need?
The first part, the basis of x gives us can express every element in x, basis of y can express every element in y, and then you
And since y is a big Y, there exist scalars in a similar fashion, alpha n plus 1. Here, if you're proving this, it's very convenient for you to be careful with the naming, because then if you use sigma notation and you split it up, you'll be like, okay, well, these are scalars, so we can just name them whatever we want, and then get it back, and then have some certain index. So you'd probably want to use the same alpha and just continue from alpha n plus 1 to alpha n plus m, such that alpha n plus 1, y1 all the way to alpha n plus m, ym is equals to y. Yeah?
So you're just writing them out as linear combination.
Yeah, because x1 to xn is a basis, y1 to ym is a basis, right? Okay. So, x plus y is equals to alpha 1, x1 plus alpha 2, x2 plus alpha n, xn plus alpha n plus m, ym, and so x plus y is in the span of, I'm worrying about who can see, x1, xn, y1, ym. Are we done? We showed the two things that we want to show. But, well, how can we conclude? Yeah.
For prove the spanning set part, can I say x is a spanning set of x, and y is a spanning set of y, then the part together is a spanning set of x plus y.
That's what we're showing. That's basically the proof that we're trying to show.
Can I prove using the words?
No, you can't. This is also something else that many of you guys
So
do.
the answer in assignment always is a lot of words.
Yeah, try not to use words. If you show it like this formally, there's no way to dispute it, right? There's no way you could get marks deducted. But if you show it in words, that could be very flimsy. Yeah.
You just pick the scalars.
I'm sorry?
You just pick the scalars, right? Or are we trying to prove the other way?
Yeah. I'm showing there exist scalars, right? As long as there exist scalars to express as a finite linear combination for any vector in x plus y, then we're good, right?
I'm asking, you have to show, like, you know how we show containment from one side, you have to prove the other way as well as the other.
No, as long as we can show it in this time, because we implicitly showed containment in the other side when we showed that it's linearly independent. And so once we show linearly independent and then spanning set, we have a basis, right? Once we have a basis, it gives us a dimension, right? And so that was the third thing that we finalized with. We just say, hey, we showed this linearly independent, we showed it's a spanning set, and so this is a basis, right? Therefore, B is a basis for x plus y. So dimension of x plus y is equals to m plus n, which is equals to dimension of x plus dimension. Okay?
QED.
All good?
QED.
QED, sure. Well, do you like QED or the box more?
The note seems
Oh,
box.
box.
The nose? Okay, which one's like a mic drop? Which
QED.
one are we?
Smile
QED?
face.
What's up for QED?
In A37.
We just have one QED level.
QED and a box.
QED in a box. QED in a box. This is a new.
In A37, in A31, if we didn't write the QED, we'll lose marks.
Lose what? Draw what?
Lose marks.
Oh.
Oh, just box, yeah.
He's saying we lose marks in A31.
If you don't write QED. Oh, but what were you proving the effect?
Wait, is Catherine catching up?
Anyway, let's not waste time. I think we're done with all the pre-midterm stuff, minus linear transformations. We'll go through that quickly after a 5 to 10 minute break. I don't want to spend too long, maybe 10 minute break, I'll see. But yeah, we'll return at most 10 minutes from now. So 7:05.